Welcome to this class. In the last class, in this module on reaction equilibria, we saw one of the fundamental relationships for reaction equilibrium, and that happens to be for an independent reaction the sum over I nu I, which is the stoichiometric coefficient, mu I, which is the chemical potential of that species I, the product of that and summed over all I, that equals 0. And we also said that if there are R independent reactions that occur in our system, then we will have one such equation for each of the R independent reactions, and therefore R such reactions will define that system at equilibrium. This is one of the very significant results, equation 614. It is very nice and compact, and it is good to remember this. This will automatically become a part of the memory. The recall is very easy for this equation. What we are going to do next is to look at phase rule for reacting biosystems, and the way we are going to do that is through some sort of an interactive method. We have already derived the phase rule for non-reacting systems in the previous module, and what I am going to do is give you some thoughts again on the background to that, and I will give you all the data and then let you come up with the phase rule for reacting biosystems, and I will give you time for that in this class. If you think about, or if we recall the phase rule equation 5.7, and that gave the number of degrees of freedom. In other words, the number of degrees of freedom is the number of independent variables that are required to complete the description of the system. We saw that the phase rule for the non-reacting system was F, the number of degrees of freedom, is C minus pi plus 2, C the number of components in each phase of the system, pi the number of phases. This was our equation 5.7 in the previous module. Let us recall that we arrived at the phase rule by considering the difference between the number of available variables and the number of independent equations between such variables. In the case of a system with reactions at equilibrium, the number of variables is the same, pi into C plus 1. There are no additional variables that are there, where, as mentioned earlier, pi is the number of phases and C is the number of components, and the number of independent equations between the variables is pi minus 1 equalities of temperature. Recall that T alpha equals T beta and so on. So if there are pi phases, you could consider that one composite equation as pi minus 1 equations or equalities of temperature. In a similar fashion, there were pi minus 1 equalities of pressure, that corresponds to equation 5.2, and pi minus 1 equalities or equations of chemical potential for each component, and we can write one for each component, and therefore the total number of such equalities of chemical potential is C into pi minus 1. So all this remains the same even for a system with reactions at equilibrium. The only additional thing is that for a reacting system with R independent reactions, we have R conditions of equilibrium of the form sum over I nu I mu I equals 0. I am going to leave you with this background. This is more than enough background to derive the phase rule for reacting biosystems. Please go ahead and do it. It can take about 15 minutes since you are doing it for the first time. It will give you a lot more confidence in the material itself. Go ahead and do it, and I will present the solution or the phase rule for reacting biosystems after about 15 minutes. Go ahead. Okay. So, we all know the background, the number of variables in the reacting system at equilibrium, the number of independent equations between the variables, all this is same as the case of the system without reactions. The only additional thing being these are conditions of equilibrium of the form sum over mu I equals 0. So, how did we go about deriving the phase rule earlier? We looked at the total number of available equations, which is pi minus 1 into C plus 2 as for the case without reactions, plus this R, and the number of variables minus the number of available equations, available independent equations between those variables actually gives us the degrees of freedom that we saw. Therefore, f, the number of degrees of freedom, is pi into C plus 1, the number of variables, minus the number of equations between them, independent equations between them. If we rearrange this, essentially some algebra, we would get C minus R minus pi plus 2. So, as you can realize, whatever was C earlier can be replaced by C minus R. So, C minus R minus pi plus 2, hopefully you got this in your own efforts, gives the number of degrees of freedom in a system with R reactions. Let us call this equation 615, and the, as can be seen, the number of degrees of freedom reduces by the number of reactions compared to a non reacting system. See you in the next class.